All right, this is part 2 of the video. I did end up having part 1 before, so hopefully look at that first. Um, I did this simple part to get the first video under 30 minutes, and I think you're going to see why at this point. So this is my sneaky, underhanded way to solve this problem, where basically if you have a solid cylinder, you think about the equivalent mass of the cylinder, and it's less because the moment of inertia is less than mr squared. I do need to put one other thing in here for to solving this a little more conventionally and with way more algebra. And that's that assume radius of the pulley is r. So it's a pirate. So here's the difficulty. If you're going to use a traditional method with this, and this has mass, unlike many situations where this doesn't have mass, this and this will not have the same tension, and that makes it a pain. So I'm going to call this T1, tension 1. I'm going to call this T2. Now we know because this is connected and going over the pulley and connected to that, there's an acceleration constraint. So that acceleration is the same as that acceleration, which is related clearly to the angular acceleration on the outside of that mass. Now the problem with it is, God, I wish this would be a little better. Oh well. So the problem with it is this. We've got to think about both rotation and linear, and then we've got to somehow put one of these in terms of the other one. So overall things to think about. Angular acceleration is net torque over moment of inertia. The other thing that we're probably going to want to remember is that angular acceleration is equal to linear acceleration divided by r, or we could say linear acceleration is equal to angular acceleration multiplied by r. I talked in one of my earlier problems about why those are pretty important to think about. So I'm going to start with figuring out the acceleration for this and this as independent equations. So I'm going to think about this one first, and I'm going to say for that, the force down is mg. The force up is tension 1, and that will equal the acceleration of that system, which still has a mass of m. So that's m times a. Now the interesting thing about that is this really, we're using Newton's second law a bajillion different ways here. So this whole problem, both with the way that I did it before and here. So, I need to be careful. This is T1A. So now what I could say is I could add T1 to both sides, subtract MA from both sides, and I could say, or T1 is equal to mg minus MA. Okay, that's going to come into play a little bit later. So I've got this kind of down, and I also am going to say that now for this system, the only thing causing this to accelerate is tension 2. So I could say my F net here is T2. I've got a mass of 2m that's accelerating. God, that really does bother me. Anyhow, 2m times a. Same acceleration here as we have here. So now what I can also do is I can think about this as that MA is equal to T2 over 2. Why is that important? Well, I've got MA over here and I've got MA up here, and that's going to be fairly useful to think about. Okay, so in fact, I'm going to set those two equations equal and say that mg minus T1 is equal to T2 over 2. So I'm going to pull this and this together. And so now I could say 2mg minus 2t1 is equal to t2. So I've put t2 in terms of t1. I think that's going to be fairly helpful. So now I'm going to kind of go back and I'm going to think about this part. I'm going to think about this angular part. Well, and this part right here, actually. So I'm going to move this over. I'm going to say, what the heck is causing the net torque? Well, the net torque is caused by a force acting perpendicularly at a radius. I know the radius of this is r. So I'm going to say this torque is going to be greater than the torque up here pulling back because the acceleration is going to be to the right and down. So I'm going to say T1r minus T2r, and that's going to be over the moment of inertia, which for a solid hoop, or pardon me, a solid cylinder, is going to be 0.5 mr squared. Now that's looking a little bit annoying, right? But I can actually go back and use this, which I put right above here. If I want to put this in terms of linear acceleration, which is what I'm going for down here, then I take all this and multiply it by the radius. We're going to see that that's actually kind of a nice thing. So A is equal to T1r minus T2r over 0.5 mr squared. Now we're going to multiply that by r. That's this coming back down. Now if you look, all these terms have r. They're multiplied by r. I get r squared. I have r squared in the bottom. So I could say A is equal to T1 minus T2 r squared over 0.5 mr squared. I love when things cancel out. I'll do that in green. So now what I can say is A is equal to T1 minus T2 over 0.5 m. But if I think about this, I've already solved for T2 in terms of T1. So I'm going to get rid of that variable. So I'm going to say T1 minus, this is what we had for T2 over here, 2mg minus 2t1 over 0.5 m. So now what I can do, minus a negative is the same as a positive, so I'm going to say A is equal to 3t1 minus 2mg over 0.5 m. Okay, well now what? I've got a lot of variables still. I've got m and g and t in here, and that does not look like something that I want. That does not seem to be a fundamental variable. But if I go way, way, way back up here, if you remember, I had that T1, when I rearrange this, was equal to mg minus ma. So I'm going to put that in here. A equals 3. Because I did it in red up here, I'll do it down here. Mg minus ma minus 2mg over 0.5 m. All right, got a lot of m's. I'm pretty sure I'm going to be able to cancel some things out there. So 3mg minus 2mg is just equal to mg. And I've got 3ma. So A equals 3mg minus 2mg minus 3ma 0.5m. So now we're getting there. A lot of m's in there still, so I guess I could cancel those out now. And I will use purple. M, 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 M. So I get 3g minus 2g minus 3a. So a is equal to g minus 3a over 0.5. So now I'm going to multiply both sides by 0.5. 0.5a is equal to g minus 3a. Add 3a to both sides. Or pardon me. Yeah, I guess I could do that. .5a is equal to g over 3.5. Holy camole. That's a lot of algebra. And you couldn't even see the last part of that. I apologize about that. That's great videoing, Doug. Let's see if I can get up there a little bit better. So, again, just to kind of do this last step if you couldn't see it, T1 I'd solve for up here. So I substituted that in red, canceled the m's out, ended up with 3g minus 2g minus 3a, so that's g minus 3a over 0.5. Multiply both sides by 0.5, or multiplied, yeah, both sides by 0.5. 0.5a equals g minus 3a. G, move the 3a over here, add it to both sides. G equals 3.5a. A equals g over 3.5. Notice that that's the same as this. This took about a minute and a half. So that's kind of, and this took 12 minutes, and that was with planning it. So I wouldn't do this way. I would think about this equivalent mass. All right, let's go ahead and do the last one. So people had asked for a bit of a torque problem. Determine the net torque and angular acceleration of a uniform bar mass 0.5 kilogram. And then qualitatively, how would the angular acceleration change if the force in the left end was placed at a 30-degree angle? So basically that's saying if it goes up like that, and we'll talk about that in a minute. So at this point, I don't think I need this anymore. I think I can do that. Make it a little taller. You can see the whole thing. Ish. Okay. All right. So what I do, I've got this at 25 centimeters. I've got this 75 centimeters here, 10 newtons and 8 newtons. So I'm going to think of this as my fulcrum. My axis of rotation is another way to think about it. So net torque. Perpendicular force multiplied by this distance would cause a counterclockwise torque. This force times this distance would cause a clockwise torque. So over here then, ten newtons multiplied by 0.75 meters minus 8 newtons times 0.25 meters. And again, remembering, I think the formula on your formula sheet, which I have as M15, is tau is equal to R cross product F, meaning it's RF sine theta, something like that. But these are both perpendicular. So 0.75 times 10 is 7.5 Newton meters. minus 8 times 0.25 is 2 Newton meters. T net, 5.5 Newton meters. That's a lot easier than the last one I just did. So now to find the angular acceleration, T net over I. All right, so this gets a little tricky again. It's another example of the parallel axis theorem. Again, don't know if I'm spelling that right. Hopefully it's blurry enough you can't tell. But this is not rotated about its center of mass. So I'm going to say that the total moment of inertia is I about the center of mass plus I extra. And if you recall, we had said that that was going to be the mass of the system times d squared. And that distance is the distance from the rotation to the center of mass. Well, in that case, since it's rotating at 25 centimeters and the center of mass is at the middle, this would be 0.25 meters would be what our d would be here. Okay, so to find the this is 1/12 ml squared, and this is going to be md squared. Okay, 1/12. The mass was given as 0.5 kilograms. Length of a meter stick, 1 meter. Mass, 0.5 kilograms. D is 0.25 squared. So I'm going to plug these in. 1 squared is 1 times 0.5. It's 0.5 divided by 12. I'll have this in the decimal. This is 0.0417. And this is a quarter squared. 1/16 times a half should be 1/32. Which it is. That's 0.303. So the overall moment of inertia is equal to 0.073 kilogram meters squared. So now I'm going to put these together. 5.5 Newton meters divided by 0.073 kilogram meters squared. It's going to be a fairly high number, actually. Yeah, 75.4 radians per second squared. Probably shouldn't be that precise since that was only given as 1 sig fig. And this is only 1 sig fig, but I don't think they're going to be worrying too much about that this year. All right, so that's its angular acceleration, and it would be positive because it would be counterclockwise. Again, I think they won't ask you that, but traditionally counterclockwise torques are positive and clockwise torques are negative. So down here, how would this change if we did something like this? Now, if this was 30 degrees from the vertical, so if we did something like that instead, well, in this case, the vertical component of this would be cosine of 30 times 8 newtons. So, you know, that's going to be a little less than 7 newtons of force there, I think. So somewhere around that. So overall, qualitatively, how would this acceleration change? Well, this torque is the same. This torque is less. So our net torque would increase. Our moment of inertia would not change. So how would it change? Would increase to a greater net torque with the same moment of inertia. You want to write that out. So a lot of times if you had something like this is a 2-point question, yeah, you've got to get that right, but you've got to explain it pretty well also. Greater torque, same moment of inertia. That explains why angular acceleration is greater. So anyhow, I think that's it. Again, I'll take pictures of these.